As we start exploring gases and looking at properties and other relationships, one interesting relationship that has been explored is the relationship in gases between things like pressure and volume, or pressure and temperature, or temperature and volume, or the amount of gas and temperature, or the amount of gas and pressure. And all of those relationships, people through the years have studied them and have determined that there are specific relationships that happen. And since there are specific relationships, we can look at formulas and quantitatively study or determine properties of gases. So the purpose of this scribblecast is to look at something called Boyle's Law. I like Boyle. He's an Irishman. I'm half Irish, so like that one. Anyway, he explored the relationship between pressure and volume of a gas. Let me show you a picture of the guy. There he is right there. Nice looking Irishman. Anyway, quite an influential man, and the relationship between volume and pressure was just one thing that he looked at. Now, if you take a look at these two pistons that I've drawn, take a look, and in each of them is the same number of red dots. Same number of red dots. And I want you to think about the volume of this one compared to the volume of this one. It almost looks like the second one's half that of the first. And then I want you to think what pressure must be being exerted on that piston as a result of the decreased volume. And what kind of relationship there would be. If I half the volume of something, what does that do to the pressure that's being exerted on that particular piston? Boyle explored that. And what he did is he set up an experiment, and he kept the same number of moles of gas, kept the same temperature, and then he changed pressure and volume. And this is sort of what he came up with. These are actual numbers that Boyle, handsome-looking Irishman, came up with. So he came up with, if the volume was 48, he found the pressure to be 29.1 millimeters of mercury. He decreased the volume to 40, notice the pressure went up by a little bit. Decreased the volume again, the pressure again went up. Now, if you take a look at these, and try this on your calculator, just take this number and multiply it by this number. That's what P times V stands for. And you'll notice that in every case you get a number that's very, very close to being the same number. And that's the relationship that he came up with. So he said, given a constant temperature and a constant number of moles, the product of the pressure and the volume of any system will be a constant. Now, if it's a constant, then, and I won't do all the math that goes along proving it, but it means that if I start with a certain pressure and a certain volume, if I change either the pressure or the volume, I can use this relationship here to determine the other unknown. Okay, so this formula here is known as Boyle's Law. And it basically states that the product of the pressure and the volume of any gas is a constant. So if you keep the temperature the same, keep the number of moles in there the same, then if I know that what that constant is, given either a new pressure or a new volume, I can solve for the other. Let's try a couple questions. Okay, so I guess here's Boyle's Law again. Just one thing before we start a question, I guess. Typically we use kPa, but we can, in this particular formula, use any unit of pressure that we want. And typically we use liters, and we're often given either milliliters or liters, so keeping that consistent is fine. We will see in another formula a little bit later, the ideal gas law, that we have to have pressure in a certain unit. But for these first few laws, it's we can use any one. Typically we're going to use kilopascals. So. Okay, except this question, where we've got atmospheres. Okay, so here's a question. Sample helium gas has a pressure of 3.54 atmospheres in a container with a volume of 23.1 liters. Okay, so that's initial stuff. Then it's transferred to a new container, same temperature, same number of moles, and the pressure is measured to be 1.87 atmospheres. Notice it started there, now the pressure is way down. So I'm assuming that I made the tank bigger. I don't know about that, but I would think so. Okay, so assuming constant temperature, no mole loss, what is the volume of the new container? So here's Boyle's Law, Boyle's Law. Initial pressure, initial volume, final pressure, final volume. Notice what I did here. We're going to be exploring relationships between all of these constants, but it's a really good idea when I'm faced with a pressure question like this, is to write some unknowns like this, where it says what's the first volume, pressure, temperature, number of moles of the gas, and then what's the final volume, pressure, temperature, and moles. And then just fill them in. So in this case here, pressure 3.54. Here's pressure, 3.54 atmospheres. Okay, container volume 23.1. So volume 23.1 liters. Then it says assume constant temperature, no mole loss. So constant temperature, so this doesn't change, this doesn't change. No mole loss, this doesn't change, this doesn't change. So these aren't even factoring in this question. And then they say the pressure is 1.87, the final pressure is 1.87 atmospheres. And the question is, what is that volume? Okay, so if you use this kind of little chart, it often helps you determine which formula to use, whether it's Boyle's or Charles or Avogadro's, whoever. But it also sets things up so it's easy to plug in. Looks like I'm solving for V2, so in solving for V2, I might as well do that first. I'm going to divide by P2, and that's equal to V2. I'm just going to rearrange that so my unknown is first. Again, you don't have to, but I like to do that. Now I plug in what I know. P1, 23.1 liters times V1, 3. Oh, did I get that backwards? Yeah, I did. Let's fix that. Pressure 1 is 3.54 atmospheres times volume 1, 23.1 liters, divided by pressure 2, 1.87 atmospheres. Notice that the atmospheres are the units are the same, so they'll cancel out, and regardless of what unit I used, it would cancel out. Okay, trusty handy dandy calculator. I'm just guessing. I'm calling it 47, but we'll see. 3.54 times 23.1 divided by 1.87. Go. Oh, I was out. So my final volume will be 43.7294,118, etc. liters. But I want to express this in the right sig figs. 3 sig figs, 3, 3, I need 3. So 43.7 liters. That would be the new volume of the tank that gas was transferred into. Let's try another Boyle's Law question. Sample neon gas, let's just fill things out as we go. Pressure 7.43 atmospheres. 7.43 atmospheres. Container 45.1 liters. Transferred to a new container with a volume of 18.4 liters. Ooh, 18.4 liters new volume. So they're squishing that in, eh? So the atmosphere's got to go way up. I'm multiplying that by maybe 2.5 or so. So that my atmosphere, my pressure's got to at least double. I'm calling 14, I'm calling 17. I'll just write that down. That's my guess. Okay, but it should be something like that. Okay, so this is what I'm looking for. Assume temperature, number of moles are constant, so I don't need those on this particular question. Let's rearrange the formula solving for P2. Hopefully you're getting comfortable at doing that now. So P2 is equal to P1, 7.43 atmospheres, times V1, 45.1 liters, divided by V2, 18.4 liters. My liters cancel, leaving me with my answer in terms of atmospheres. So it'll be atmospheres. And now I need to bring out the calculator. Here we go. So 7.43 times 45.1 divide 18.4 equals, oh, I was just off again. I guess 17, yeah, it was close, but the correct answer, 18.21157, etc. We check back our sig figs. We look like we have 3 everywhere, so our final pressure is 18.2 atmospheres. Okay, you getting the idea? Oh, one final thing that they did in this question. This is a little dirty. Oh, I like that. Yeah, I'd ask you a question like that. So the first part of the question says, what's the new pressure? And they asked for atmospheres, and that's what they had given me, so that's easy to figure out. But then they say, hey, what's that pressure in kilopascals? Well, then all we'd have to do is go and say, I can do that with my dimensional analysis. I write 18.2 atmospheres, and if they want that in kilopascals, I multiply it by, I know from those conversion units that I did before, hopefully you wrote those down somewhere, that 1.000 atmospheres is the same thing as 101,325 pascals. And so now I can take the answer that I just got, 18.211, and times that by 101,325 pascals. Well, that's a big number. Equals 1,845,287 pascals. But let's convert that to kilopascals just by moving over 3. So it'd be 1,845.287 kilopascals. Oh, but I only have 3 sig figs. So I need to round this to 3 sig figs. This is my third one coming from this side, so I have to round to this one. 1/8. Okay, the one pass is 5 or more, so this one goes up to a 5. Everything else gets 0. So 1,850 kilopascals. Or, I guess I could write it as scientific notation, like that. So move the decimal over 3, 1.85 times 10 to the third kilopascals. I guess, just while we're into writing things in different formats, if I have 1,000 kilopascals, that's 1 megapascal. So I could call it 1.85 megapascals. That sounds a little funny. I'd probably leave my answer there or there. Okay, so that helps you in looking at the relationship between pressure and volume. That's Boyle, our old Irishman. Now, one thing, just as we're going to look at other relationships too, one thing that we often do, rather than giving you a certain atmosphere or a certain pressure or a certain temperature, people have come up with a standard for those. And there's actually a lot of standards, and the standards seem to change every couple of years. But in the research that I did, this is what I came up with. That so rather than saying, hey, this is the temperature, this is the pressure, usually in a question we'll just say, hey, this is the standard temperature and pressure. So we'll say, hey, such and such a thing is at SATP. If we say SATP, what that means is standard, I think it stands for ambient temperature and pressure. But what that's given me is that the temperature is 25 degrees Celsius and the pressure is 100 kilopascals. If I say standard temperature and pressure, or STP, not to be confused with the oil, so if I just say STP, that means the temperature is 0 Celsius and 101.325 kilopascals. Okay, so often a question might just say a certain gas at SATP, As soon as they say at SATP, you know exactly where the temperature and the pressure are of that gas. Okay, hopefully that gives you a bit of understanding of Boyle's law. He was the guy that related pressure and volume. If the pressure goes up, the volume must be going down. Or if the pressure goes down, the volume must have gone up. So that's the relationship that he explored. In the next section, we'll look at Charles's law, who explored a different relationship.